Okay, welcome back to Real Analysis. In section 5.2, we're going to discuss properties of limits, each one of which is sort of analogous to a property of limit of sequences that we looked at back in chapter 2. And in fact, the sequential criteria for limits is kind of going to be the device that we're going to use to prove all of these properties of limits. All right. So in particular, let's recall that sequential criteria for limits. I've got it written here in bold, the preamble for it, and we'll assume this everywhere in the lecture, that we've got some subset of the real numbers called E, some function defined on it, and then we take some accumulation point of that set and some number called L. Okay, those are just sort of the necessary ingredients for us to have to be able to speak about this limit as we've defined it. All right. And the sequential criteria for limits says that in particular, that a necessary and sufficient condition for that limit to equal L is that for every sequence that you take in E, the sequence terms never have to be equal to the limiting point x0 itself, the accumulation point x0 itself. But for every such sequence that converges to x0, the image sequence converges to L. All right. So that's what we're going to call our sequential criteria for limits. And kind of the gist of this whole lecture, I'm going to kind of do some things explicitly for you and then kick a lot of it to you and hope that you'll practice these ideas yourself, is that you can basically transfer any property about limits of sequences, that is all the material from sections 2.4 to 2.6, you can transfer those to properties about limits of functions using this sequential criteria for limits. Right? So that's what I want to illustrate in this lecture. Rather than kind of writing it every single time that I have a proof statement about limits, I'm just going to declare once and for all that everywhere in this lecture that E is some subset of the real line, F is a function defined on E, X0 is an accumulation point, and L is some real number. All right, so I'm just going to kind of globally quantify those expressions and variables once and for all to avoid kind of repetition and make the exposition of the video a little bit cleaner. Okay, so let's take a look at our first result. This is analogous. We have a uniqueness statement for sequence limits of sequences. So I want to show you how you can convert that into a uniqueness statement for sequence of functions. All right. So given our preamble, everything about x, 0, e, and so on, that if you have some function that has a limit L at x0, then L is unique. And that is that you can't have some other distinct value that's also equal to the limit. Okay, typical uniqueness proof. I'm going to start off by saying, well, suppose I have two numbers and that they both equal the limit of this function f at x0. Okay, rather than giving an epsilon proof, you can try it. You can certainly write a definition 5.1 based proof of this, but I want to illustrate this sequence technique. So I'm going to take a sequence xn and e that doesn't have any terms equal to x0, and it converges to x0. I can always do that because x0 is an accumulation point. Okay, so there's always such a sequence. And then using the sequential criteria, well, if we're assuming that the limit as x goes to x0 of f is L1, then the sequential criteria says that the image sequence f of xn converges to L1. But likewise, if the limit as x goes to x0 is also equal to L2, the sequential criteria says that the image sequence also goes to L2. So then I just apply the uniqueness for sequences, theorem 2.8. It says that L1 and L2 have to be the same. Nice. So I don't have to really recapitulate it. I can just sort of apply the corresponding property for limits of sequences applied to the image sequence here. Nice. Let's try another one. I think your author of the book, authors of the book gives the proof of this using the epsilon delta definition of limit. I'm going to do it with sequences. So what does it say? If you take same preamble, if some function has a limit L at x naught, then it's saying that there's some interval around x naught, a neighborhood of radius c in our language, and some number m such that the function is bounded by m on that neighborhood. Okay, so it's a bound. If you have a limit at a point, then you're bounded in some neighborhood of that point, or you're bounded at x in our previous language. All right, so I'm going to kind of set this up as a contrapositive proof. Where are the quantifiers? It's saying that there exists some interval and there exists some number m. So if I'm going to do this by contrapositive, I'm going to say, well, suppose for every positive number c and for every positive number m, I can always find an x in the domain of this function in the c neighborhood of x0. And I can always choose x to be something other than x0. Because f of x0 is just some value, and so it's it's one and only output value. So I can always find some other input, an element of the deleted neighborhood of x0 of radius c that the function value exceeds m, and I can do that for every m. All right. Well, then if I choose strategically for any natural number, if I take c to be 1 over n and the number m to be n itself, then I can always find some point, I'm going to call it x sub n because it depends on n, in the 1 over n radius deleted neighborhood of x0 and e, the domain of this function, and its function value is bigger than n. So by construction, we've seen this construction several times now, so I'm not going to dwell on it. This is a sequence in E, none of whose terms are x0, and it converges to x. You supply the details. It's in a 1 over n neighborhood for every n. But the image sequence for every n, f of xn is greater than n. So that image sequence diverges. It can't converge to something if its nth value is bigger than n for every n. It's actually converging, it's diverging to infinity, right? So therefore, the sequential limit criterion says that this limit can't exist. Yeah, because I've got a sequence converging to x naught, but the image sequence diverges. So the sequence can't. It's by the divergence criteria, if you like. This sequence, this limit can't exist. So that proves theorem 5.11 by contrapositive. If the limit exists, then the function must actually be bounded on some neighborhood. Cool. These proofs are going pretty smooth. It's because of all the work we did in chapter 2. We built this very, very solid foundation of sequences. And so we're just kind of translating all of that work into statements about this new context. Here's a third one, bounded away from 0. So what does it mean? If the statement is saying that if you take some function with a limit, that limit exists and it isn't 0. All right, so if you want me to write that in kind of to narrate here, this limit exists, but oops, I didn't mean to write that. Sorry about that. I mean, the limit exists, but it's not 0. Then there's some neighborhood around x naught, radius c, and some positive number little m, so that the function is greater than or equal to little m. The m is positive, so there's some neighborhood around x naught on which your function is positive. Your function in absolute value is bounded away from 0, as they say. So that's going to be true for every x in the neighborhood. All right. Well, why every x naught not equal to x naught? Again, the limits are never about what the function's value is at x naught. X naught doesn't even have to be in the domain of this function f. Okay. So I'm going to do this by a kind of a contrapositive argument as well. There's two existential quantifiers. There exists some c and there exists some positive number m such that something happens. So my proof is going to say, well, suppose not. Now, suppose that this limit exists and is equal to L, but suppose for every C and every positive M, I can always find something in the deleted C neighborhood of X naught and E whose function value is less than M in absolute value. Okay, so I'm just negating the conclusion of the theorem there. Okay, well, so once again, if I can do that for every C, then I can choose C to be the reciprocal of any natural number. It's for any positive number m, I can let m be the same thing. That's a positive number, 1 over n. And I can always find something that depends on n. So it's in this deleted neighborhood of x naught. It's also in the domain of the function. Sorry, let me just sort of squeeze that in there. This xn is also in E, and its function value in absolute value, f of xn, is no more than 1 over n. So you supply the details, but that sequence is a sequence in E, none of whose terms are x naught, and it converges to x0 because the nth term is in a 1 over n neighborhood of x0. And so by the sequential limit criteria, the image sequence converges to L, right? I'm assuming that this limit exists and I've got a sequence converging to x0, so its image converges to L. That's what the criteria says. But we know that the absolute value of xn is less than 1 over n for every n. So that would be a direct epsilon argument. That image sequence is converging to 0. Well, the limits are unique. We just proved it in this section. So if I have a sequence f of xn converging to L and converging to 0, then L has to be 0, right? So that's by the theorem that we opened this lecture with, right? So the result now follows by contrapositive. If L isn't 0, then there must be some neighborhood around which f is bounded away from 0. Okay, cool. So I'll kind of let you pause the video there and soak that in, but hopefully you're getting some appreciation of what I mean by I'm taking this property of sequences and kind of translating it into a property of functions. So to kind of summarize that here, each one of those proofs showed how I can use the sequential limit criteria to take some property about sequences and write the kind of corresponding property about functions. And to write the proof, I just sort of take the property about functions, convert it into that sequence converging to the accumulation point in the domain, apply the appropriate sequence theorem, and then conclude that that means something about the limit of the function. All right, everywhere in the proof, I said this before, but x0 being a cluster point of E always guarantees that we can take such a sequence. We can take a sequence, none of whose terms are x0, that converges to x0. All right, so then you just take the appropriate sequence property, maybe it was the uniqueness, so on. I've got more examples below. You apply it to that image sequence. All right. So we're going to just kind of walk through, I'm not going to give the proofs, but we're going to kind of walk through lots of the theorems that we saw back in chapter 2. And in each one of these things, you could kind of use this recipe to supply a proof of these theorems. Of course, you could give direct epsilon proofs as well. The author of the text kind of mixes it up a little bit. In your exercises, I'm going to ask you to mix it up a little bit, but every one of these things lends itself to a so-called sequential argument. I can use the sequential criteria for limits to provide proofs of all of these things. I highly recommend, maybe as you're watching the video, to stop and kind of at least sketch out these arguments as you go. So I'm not going to include the arguments. This is just sort of more of like a shopping list. All right. Well, one of the very first limit things that we proved past the uniqueness of limits was that if you multiply a sequence by a constant, the resulting sequence will convert a convergent sequence. The resulting sequence converges to that constant times its limit. Well, the same is true for functions. So the author is calling it the multiples of limits theorem, that if you have some function and its limit exists, then if you take any real number and you multiply that real number by the function, that new function also has a limit, and its limit is c times the old limit. All right, so you can pull constants through limits, calculus students usually say. How to prove that? Take a sequence converging to x naught, apply f, use the chapter 2 multiples of limit theorem, get your desired conclusion. Nice. A second theorem that we looked at, sums and differences, right? For sequences, you take two convergent sequences. If you add or subtract them, the resulting sequence converges to either the sum or the difference. Well, the same is true for functions. So the notation is just saying if you take two functions f and g, they both have limits. You take an accumulation point of, here you have to be a little bit careful. This has to be an accumulation point of the domain of both f and g. So the author is using DOM of F for the domain of F, and likewise for G. So it's just kind of a technicality that X0 needs to be an accumulation point of the intersection of those two things. That's only so that it makes sense to speak about the limit of F plus G and F minus G. But the theorem says that, yeah, the limit of the sum is the sum of the limits. The limit of the difference is the difference of the limits. Why is it true? Because it's true for sequences. And these limit statements are equivalent to statements about sequences. Maybe you can stop and write the proof out, write out the details. Okay, everything, products, quotients, take two functions, both of which have limits. The limit of the product is the product of the limits. Here again, X is accumulation point of the common domain. Same thing for quotients. X is an accumulation point of the common domain. And of course, the quotient has a caveat. That the limit of g is not 0. right? So that's always the case when you're talking about limits of quotients, that you have to assume more than the limit just doesn't exist. It can't go to zero, because otherwise the right-hand side of that formula there at the bottom of the screen doesn't make any sense. What's the proof? It works for sequences, so it works for these limits by the sequential limit criteria. Nice. I know I'm going fast, but it's not the point to kind of rehash all of this stuff. The point is to just sort of say that everything we know about limits of sequences holds for limits of functions. That's courtesy of the sequential criteria for limits. Here's a couple more. Maybe they won't both fit, so I'll just sort of reveal them one at a time. Order properties as well. So those previous theorems were all back in the section that was called like algebra properties of limits. There were also order properties of limits. If you take two functions with limits, x is an accumulation point of their common domain, and one function g dominates f, then the same is true for the limits. Just like with sequences, you can't write a theorem that says if this is strict, then this second equality will be strict. It doesn't work that way. You should be able to give an example of that. But that order property for sequences transfers over to an order property for functions. The squeeze theorem. You take three functions, f, g, and h. X is an accumulation point of the common domain. Here, the way the author's writing, f and g are functions on E. I mean, so x0 is just a accumulation point of E. Right? F and G have the same limit, and H is always between F and G. Well, then H has that limit. It's squeezed between them. It has to be so because it's true for sequences. This one, I actually am going to make one of your formal homework problems. I'm going to ask you to write a sequential proof of this squeeze theorem for functions. Cool. Absolute values was one of our properties for sequences, so it's true for functions. The limit of the absolute value is the absolute value of the limits. Because of that, maybe you remember back in the day, we talked about these min and max functions. The min and max function are expressible in terms of absolute values. It's one of your homework problems. Yeah. The maximum of two functions is the maximum of two real numbers, rather, is kind of their arithmetic average plus their difference and so on. So you can express the min and the max in terms of absolute values. So you can kind of combine that, or just go back and use the min-max theorem for sequences. You don't even have to recapitulate all of that stuff. Nice. So one more theorem here. Let me kind of reveal it, as much of it as I can here. So I am going to give a proof of this one. So it's the last theorem that's occurring in section 5.2, and it involves an operation that we didn't apply to sequences. That is function composition. Why don't I apply function composition to sequences? Well, because sequences have inputs that are natural numbers, but their outputs don't necessarily have to be a natural number. So set theoretically, it might not even make sense to compose one sequence with another, right? But we are going to be able to compose functions with each other, and so this is going to be an important property. And the hypothesis of it uses a special property. I'll say what it is when I reveal the entire theorem down here. That special property is going to get a name. We're going to study it carefully in section 5.4. It's called continuity. Okay. But just to kind of remind you, I'm still assuming that E is a subset of R, F is a function on E, X0 is an accumulation point of E, and L is some real number. Okay, so that's still in play here. So this involves two functions, little f and capital F. So capital F is a function. It's defined at least on some neighborhood of this number L, L being the limit of little f. Okay, so I quantified little f above. It has limit L. Capital F has to be defined on some neighborhood that contains L. So in other words, there's some epsilon neighborhood of L into which I can plug all elements into the function f. So the domain of f contains this epsilon neighborhood. And I'm going to further assume that the limit, as say, I'm going to call the variable z of f of z is equal to capital F of L. All right, so that's the special property I was talking about. We'll study this carefully. Basically, what that property is saying is that the limit of capital F exists. Z is an element of its domain, and the limit, or excuse me, L is an element of its domain. let me start again. This limit as z approaches L exists. The point that I'm taking the limit at is an element of the domain of f, because I'm plugging it into f. Everywhere here, I mean capital F. And that limit is equal to the function value. So that's a special property that we're going to study in section 5.4 that we will call continuity. But for right now, let me just put it in here as this hypothesis. Okay, so if I'm assuming that, and I'm assuming that little f approaches L as x goes to x0, then I'll just let you read the formula, but this is saying that the limit of the composition is the composition of the limits. Or sometimes, like in calculus, you like to say that you can interchange limit and capital F. Yeah, so here capital F is applied to f of x first, and then you take the limit. On the right-hand side of this equality, I'm taking the limit of little f first and then applying capital F. The theorem is saying you get the same thing, and in particular, you get f of L. Okay, so let's just give a quick sequential proof here. I want to try to show for this function, capital F of little f of g. So if you, in function notation, I'm talking about the composition of capital F with little f, and I want to show that its limit as x goes to x0 is capital F of L. So to give a sequential limit proof, I'm going to start by taking a sequence in the domain E, none of whose terms are x naught, but it converges to x naught as n goes to infinity. All right. So then my goal is to show that if I plug that sequence into this composition, f composed with little f, I should get capital F of L. All right. So I'm going to first apply the sequential limit criteria to the fact that little f has limit L. So this xn is converging to x naught. So the image sequence converges to L because the limit of as x goes to x naught of f of x is L. That's using the sequential limit criteria applied to little f. Okay. Now, the hypothesis of the theorem said that capital F is defined on some neighborhood of L. So let's call that neighborhood n sub epsilon. So there's some epsilon neighborhood of L on which capital F is defined. All right, so there's some interval around L. I'm going to kind of maybe draw a picture over here and put it on a vertical axis. So here's this L, and there's some epsilon neighborhood, L plus epsilon, L minus epsilon, on which all the inputs in that thing can be plugged into capital F, right? But I have this sequence f of xn converging to L. So for sufficiently large n, for n greater than or equal to capital N, f of xn is going to eventually be in there. If I take n big enough, my sequence terms, f of xn, are going to all get in that epsilon neighborhood of L and stay there. That's because the sequence f of xn converges to L. So just to make the notation match the theorem here a little bit, if I rename f of xn zn, well, then zn is approaching L. I'm assuming that the limit as z goes to L of capital F is f of L. So then the image of that sequence goes to f of L, again by the sequential limit criteria. Okay. So if I just kind of put all that together, capital F of zn is capital F of xn, and that converges to f of L. So now to kind of wrap it all up, xn was any sequence in E, none of whose terms are x naught, that converges to x naught. F of little f of xn converges to f of L. So that precisely means, I should write it here, it precisely means that the limit as z goes, it precisely means that the limit as x goes to x naught of capital F of little f of x is capital F of L by definition. Or not by definition, but by the sequential limit criteria. Nice. Oh, I wrote it down there. Sorry, I don't know my own notes. Okay, not the best video ever, but hopefully that kind of helps you understand that proof. I'm going to end this video just by saying that there's a section in chapter 5 that I'm not going to make a video for. I'll kind of pepper some examples, I hope, throughout the class when we're meeting in live on Zoom. But it has lots of interesting examples of functions and their limits. So we're going to explore some of those in some of our examples, some of them in our homework, and some of them on discussion days. But I would strongly recommend you, I'll so strongly recommend that I'll highlight it in two different colors, to read through the examples in section 5.26 very carefully, because here I've kind of stuck to polynomial examples, absolute value examples, and so on. There's some functions in there that are a little bit more interesting. Okay, that's going to end this video, so thanks for listening.